Hello physics. This is going on your day 4 notes, and I did the sequence of days probably out of order. We probably did 1, 2, 3, then we did the actual lab, which was the day 5 activity, and now we're back finishing up this mod with information for day 4 notes. The topic on day 4 is Newton's third law. And let's recap before I actually state Newton's third law. And it turns out that we've had a couple new formulas, so we'll kind of recap them. Sum of the forces equals ma was Newton's second law. And it is stating that whenever there's a force or several forces, we're going to add them all up here on the left, and they will equal whatever mass there was times the acceleration of that mass. So these come in pairs. So force and acceleration. So if there is a force, we will see an acceleration. And if there's an acceleration, we know there has been a force. So we observed that earlier. And then we found this little guy who taught us about force normal. All he had to do was stand on the floor and not crash through it. His weight was downward, negative mg, and it was countered by force normal upward, which is provided by the surface and perpendicular to it. So force normal, and when we're on a flat surface, any object on a horizontal surface like this, force normal is mg. When we start to slant our surfaces, like for an inclined plane, this will change up a bit. But for now, force normal will be mg. Then we added the force of friction. And the force of friction, we learned, was either m mu sub s times force normal, or mu sub k times force normal. If the object was still when we started to push it, the force of friction used mu sub s. If the object was already in motion, we used mu sub k. These are coefficients of static and kinetic friction. And we recall force normal for now on our horizontal surfaces is mg. All right, so let's go back to the sum of the forces equals ma, and recognize that when we have a little person exerting a force, like here, we did some problems where we put together the sum of the forces, and there were two forces: the force of the pull or the push, and this happens to be a push example, minus the force of friction. Force of friction is always opposite motion. So we have the force of the push, and we have force of friction opposing it, always in opposite directions. And we just put that into Newton's equation: force of the pull in the positive direction minus force of friction opposing it equals ma. And we were able to put in numbers for that, and more specifically, force of the pull minus, say the object is in motion, we would use mu sub k, force normal, which is for now mg, equals ma. And we were able to solve problems with that equation. All right, that's a recap. So that leads us, as I mentioned before, to Newton's third law. So let's begin chatting about it. You've heard it before, so let's write it out in all of its glory. For every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. That is the simplicity of Newton's third law. However, it has profound implications, and that's what we're going to talk about now. So it turns out this idea indicates that forces come in pairs. So for every action, there's a reaction. So we're talking about a force in one direction and then an equal and opposite force in another direction. So we have these force pairs. We don't have one force acting by itself, but we have the forces coming in pairs. And these pairs are equal in magnitude. They have the same vector length. So the force pairs have equal in magnitude, but opposite in direction. So equal and opposite in equal in magnitude, opposite in direction. So let's talk about what it doesn't mean, because sometimes that helps us understand a little more about what it does mean. So say we have this little guy pushing a table, and say I push the table and the table pushes back on me at the point of contact. So right here where my hands are contacting the table, I'm exerting a push on the table, and the table is exerting an equal and opposite push on me. You can see where that theoretically leads to some troublesome conclusions, because if these forces are equal and opposite, then I can never move the table. The harder I push on the table, the harder the table pushes on me. So therefore there is no motion ever. We never move anything. So obviously this is wrong, and I want to emphasize that it is wrong by telling you what is correct, and this will clarify it. So turning over the page, looking at my shadows. Alright, here we go. Right. The reason why there can be motion with these equal and opposite force pairs is the equal and opposite force pairs are on completely different objects. So think about that. When the action would be I push on the table, the reaction, and first of all, what is the evidence of the fact that I push on the table? The table accelerates, it moves. So I'm going to push on my table here, and you can hear the squeaky sounds of it moving. So I push on the table, the evidence is the table moves. That's the action. The reaction is the table pushes on me. So notice the force went onto the table in the action part. On the reaction, the table's forced on me. So the force was on the table and the force was on me. Two completely different objects. So there is motion. So what evidence do we have that the table pushes on me? Well, let me push on my table here. And I will show you the evidence. Right there on my hand. Do you see that line? Okay, that is clear evidence that the table pushed on me. So the table pushed on me. There was a line on my hand, clearly evidencing, and I can feel the pressure there where it was exerting force on me. So I was pushing on the table and the table was pushing on me. So I can push the table and move it, but the table's going to push on me, evidenced by a line on my hand. So let's talk about some other examples. Say you jump on a mini tramp. So if you're jumping on a mini tramp, fooling with my lighting here. If you jump on a mini tramp, we want to talk about what is the action and the reaction, and what evidence there is for each. So when you jump on the trampoline, the action is you exert a force on the trampoline. And the reaction, and what's the then the trampoline exerts a force on you. So equal and opposite forces. Trampoline on you on the trampoline, trampoline on you. So now let's see what evidence there is. What is the evidence that you exerted a force on the trampoline? I don't know if I can draw this very well, but here's the mini tramp with the little springs that hook around it and the legs. So when I jump on the trampoline, what happens to the trampoline to evidence the fact that I have exerted a force on it? It dimples in. So that's my little dimple. So it's going to tuck in, it's going to bend in where my force was applied. So that's the evidence. What's the evidence that the trampoline exerts a force on me? Well, the evidence is, this is the action. And what's the evidence of the reaction? What is the evidence that the trampoline exerts a force on me? I spring upwards. So that is an action-reaction pair. How about these two examples, pushing on the table and jumping on a trampoline, are contact forces. There are some forces out there which do operate but without contact. So let's talk about one of those. Suppose the action is I drop a ball. So when I drop a ball, that is an action. Nothing's touching the ball, but the earth does exert a force on the ball as soon as I let go of it, when I drop the ball. So this is due to the force of gravity, and that's what is causing the force. So where is the equal and opposite force on the ball? So let's talk about that. So if I drop a ball, the earth exerts a force on the ball. And what is the evidence that gravity has exerted a force on the ball? The ball accelerates. It moves downward at more quickly every second. The ball accelerates downward. But it's harder to see what is the evidence of the reaction. And what is the reaction? So the earth exerts a force on the ball, but where is the equal and opposite reaction? The equal and opposite reaction is the ball exerts a force on the earth. And let's see if we can talk about that a little bit mathematically. Say the force of the earth on the ball force equals ma. The force of gravity, that's what the earth, it's a non-contact force, but it's still there. It's attracting the ball, pulling the ball. So the force of the earth on the ball equals ma, like every force equals ma. So the force of the earth on the ball equals the mass of the ball times the acceleration of the ball. So when we turn that around and look at the force of the ball on the earth, these have to be equal and opposite. So the force of the ball on the earth equals the mass of the earth times the acceleration of the earth. Remember, these two numbers are exactly equal. So therefore, if they're exactly equal, how large is this number? So whatever number this is, we could easily calculate the mass of the ball and the acceleration of the ball and calculate the force of the earth on the ball. The force of the ball on the earth is going to be the same number. So whatever number we get here will be here. But this number is huge, the mass of the earth. So the only way we can get the same number as we got up here is if this number is large, actually massive, then this number is extremely small. That's the only way. These two can multiply and get you the same number as we got here. And therefore, when I drop the ball is accelerating toward the earth. So the force of gravity is drawing the ball to the earth. But the ball is drawing the earth to itself. But it is minuscule. It's accelerating the earth to itself a very tiny bit. And so tiny, of course, that we are unaware of it. So anything that you drop on the earth, good old planet Earth, is drawing, any mass will have a force of gravity from itself and will draw the earth toward it, a very small amount. So that's pretty interesting. All right, we'll finish up on this video by looking at, sorry, mess with your view there. Let's look at this. All motion, let's see how action-reaction pairs can be thought of in a slightly different way. All motion is due to action-reaction, this action-reaction principles. So let's look at how that works. Suppose we have a car, and that car has the tires that are moving, and as they spin, they contact the earth. Let's say it's a gravel road, so we have a bunch of gravel, and the tires are acting on the gravel, and they are spinning the gravel backwards. As the tires turn around, they're grabbing the gravel and spinning it backwards. So that is the action. So the tires grabbing and thrusting the gravel and minuscule pieces of the road backwards. What's the reaction? The car moves forward. So even if you're not on a gravel road, the frictional grab of the tires on the road will be backwards, and it will cause your car to move forward. So let's look at that. And so I wrote that out here. Let's see. Come back, come back. The action, the tires force the gravel backwards, and the reaction, the car moves forward. Let's take that out in space. So in space, when we were at the beginning of the space program, we were wondering if this action-reaction pair actually worked in outer space. So when we go up in space and say the action is a combustion, there's a combustion in the rocket chamber, and it thrusts a force backward out of the rocket. So the reaction, we were hoping, is the rocket moves forward. So some people have this concept where if there's a rocket and there's a combustion inside and it forces, the combustion is an explosive force in one direction, say in this case to the right, that some people believe that as that combustion occurs, it's actually somehow pushing on some kind of molecules and forcing the rocket this way. That is not correct thinking. The only reason that rocket moves forward, because there are no, or very few, molecules in space, so this action-reaction pair is the only reason why, Newton's third law is the only reason why this rocket will move forward. So we have the explosive force backwards countered by the reaction pair. The rocket moves forward. So we were wondering when we first started exploring space if we understood that principle well enough, and sure enough, rockets do accelerate forward in outer space. All right, the rest of this period you'll be reading a handout out loud. Mr. DeBloom will pick some readers and you'll read through a handout that will explain this, I think, better than I have just explained it. And then you'll have a couple questions to answer in regards to that. All right, So read the handout as directed and answer the questions. And as for me, I'm done. So over and out. Carry on.